Salam everybody, let's start off with the electricity worksheet. A metal wire has a resistance per unit length of 0.92 ohms per meter. The wire has a uniform cross-sectional area of 5.3 into 10 to the power minus 7. Now, you know that whenever you're given resistance per unit length and they're asking you for resistivity, the formula for this is R is equals to rho L over A, where you have to make rho the subject and you'll get R into A over L. Now your resistance per unit length is 0.92. So they've given you that value 0.92. And what is the area? The area is 5.3 into 10 to the power minus 7. When you multiply them, you would end up getting 4.9 into 10 to the power minus 7 ohm meters. Next, a battery of EMF E and negligible internal resistance connected in series with a fixed resistor and an LDR. The resistance of the fixed resistor is 1400 ohms, as you can see. The intensity of light illuminating the LDR causes it to have a resistance of 1600. So LDR's resistance can vary, and right now at the moment it's 1600 for a certain light intensity. And at that particular instant, the voltmeter reading is 6.4. Good, so we have the voltmeter reading as well. That means I can actually figure out what the current is in my LDR, and that will also be the current in my circuit, because you know that the current is going to flow like this. So that's also going to be the current in this particular resistor. So you can use V is equals to IR. You have the voltage, which is 6.4. You have the resistance, which is 1600. And you can find out what the current is. So when you do 6.4 divided by 1600, you get 4 into 10 to the power minus 3 amperes. Calculate the number of free electrons which are passing in a time of 3.2 minutes. The number of free electrons. Now, try to understand that the formula, you already have the current, and they're asking for the number of free electrons, and they're giving you the time as well. So the formula will be I is equals to NE over T. And you have the current, which is 4 into 10 to the power minus 3 is equals to N into 1.6 into 10 to the power minus 19. This is the charge, fundamental charge, electron. And time is 3.2 minutes. So minutes into seconds is 60. So 4 into 10 to the minus 3 times 3.2 times 60. Divided by 1.6 into 10 to the power minus 19. And the number of free electrons that we end up getting are 4.8 into 10 to the power 18. I hope that makes sense. Next, calculate the EMF E. Now, look, I already told you that you have the current, which is 4 milliamperes. And you also have the same current going through the 1400 ohm resistor. So can you figure out what is the voltage drop over here? The voltage drop over here would be V is equals to IR, which is 4 into 10 to the power minus 3 times 1400. So 4 into 10 to the power minus 3 into 1400, and you get 5.6 volts. So try to understand it this way. This is a cell of EMF E. This is one LDR across which your voltage drop was 6.4 volts. Next, you had a resistor over here, a fixed resistor. The voltage drop across this resistor was 5.6 volts. So what is the EMF of the cell? You can apply Kirchhoff's voltage law, which is that in a closed loop, the sum of EMFs must be equal to the sum of potential drops. So you have one potential drop of 6.4 and you have one more potential drop of 5.6. So you add 6.4 and 5.6, and what do you get? 6 plus 6.4, you get 12. And because there's only one battery, hence you will write E over here. So the EMF is 12 volts. Determine the ratio power dissipated in LDR divided by power dissipated in the fixed resistor. Now, look, power, whenever you think of power dissipated, you have three formulas in your mind. You have IV, you have I squared R, and you have V squared over R. What's the formula that you should use in this scenario which really makes your task easy and you don't have to do many more calculations. Do you know that the current going through both the resistors is the same? So if I have power in resistor or power in LDR divided by power in the resistor, I know that the current is going to be the same. So if you look at the screen, I square resistance of LDR divided by I square resistance of the fixed resistor. And you know that I can cancel out the current squares because the current is the same. It's a series circuit. So essentially, you're doing the resistance of the LDR, which was 1600, and the resistance of the fixed resistor was 1400. So we're doing 1600 over 1400, and we end up getting 1.1 as our answer. Part C, environmental conditions change, causing a decrease in the resistance of the LDR. The temperature of the environment does not change. So the resistance of the LDR drops. Why does the resistance of the LDR drop? Because the light intensity on the LDR increases. So what happened to the light intensity? The light intensity increased. What will happen to the current in the battery? What happens when resistance falls? It's not important that one part of the circuit has less resistance. What happens to the resistance of the circuit? In the circuit, you've got two resistors. If even one of them has less resistance, the amount of current in the circuit will increase. Because you know that when resistance goes down, the current goes up. And what happens to the reading of the voltmeter? Try to understand that the resistance of the LDR has gone down. Voltage is proportional to resistance. It's a series circuit. So in a series circuit, remember, voltage and resistance have a direct relationship. Your resistance of the LDR decreased. Hence, the voltage across the LDR will also decrease. Now, some of you might argue that V is equals to IR. Listen to me very carefully. Some of you might argue, and you would say, well, did we not say that the current has increased? And we're also saying that the resistance has decreased. So why is the voltage even changing? The voltage should remain the same. Listen to me very, very carefully. It's a good question to ask, but understand it once. When this resistance goes down, when this resistance decreases, what will happen to the current flowing in the circuit? The current flowing in the circuit will increase. Make sense? So far, so good. Now, let go of this, let go of this. So there's a high current flowing. Just tell me something. When this high current flows through this resistor which had a fixed value, this did not change, right? This 1400 remained the same. It did not change. What will happen to the voltage drop in this 1400 ohm resistor? What's going to happen here? This voltage drop will also increase. Why? V is equals to IR. This should make sense to you, that the resistance is fixed at 1400 ohms. It's fixed, it's not changing. The current has increased, hence the voltage drop across this resistor has increased. Make sense? So that means instead of 5.6, you will have a higher value. Initially it was 5.6, but now you'll have a higher value. So you tell me when this voltage will go up from 5.6 to, let's say, for example, it goes to 7 volts. What's going to happen to the voltage over here? Do you think it will remain 6.4? The battery is giving you 12 volts. So that voltage is fixed. You must understand that the voltage drop across this resistor has increased, and the voltage drop across 1400 ohms plus the voltage drop across the LDR, that's what is that? That law is called Kirchhoff's voltage law, that your EMF that is being supplied should be equal to the voltage drop across the LDR, thus the voltage drop across the fixed resistor. Understand this point. For the LDR, I've got the experience, so I knew that the voltage across the LDR would drop. But if you're doing it for the first time, I would recommend that you don't do it directly, because you can't directly conclude about the voltage of the LDR. Why? Because the voltage of the LDR depends on the resistance of the LDR and the current in the LDR. Correct? And the resistance of the LDR is changing. It's decreasing, the question said. The current in the LDR is also changing because we know that the current will be more. So you can't directly jump to a conclusion. Both of these things are changing. So you can't say that the voltage will increase, decrease. You need a fixed or a constant value to make a conclusion. Like for example, for this resistor, I can very fairly say, and I'm sure you can also very fairly say, that yes, over here we can apply V is equals to IR. Resistance is constant because it's not changing. So if the current in this resistor is higher, the voltage will be higher. There is no discrepancy. No discrepancy. So if we all agree that the voltage across the fixed resistor has increased and the EMF is constant, what should happen to the voltage across the LDR? Because both of them add up, both of these values add up to become equal to the EMF, and the EMF is constant. So the voltage across the LDR decreases. So I've told you two ways. One way is that you could simply say that the resistance of the LDR has gone down and resistance is proportional to voltage, hence the voltage across the LDR decreases. And why? I have just explained it to you over here. So that is a long answer to the short question, that the reading of the voltmeter, because the voltmeter is across the LDR, hence that voltmeter reading will decrease. Next, state Kirchhoff's second law. Now, Kirchhoff's second law, you must remember the names. The first law is the current law, and the second law is the voltage law. And that's exactly what I was telling you above as well, that the sum of EMFs in a closed loop is equal to the sum of potential drops in that loop. The same thing that you were applying, the same principle that you learn at O levels, that in a series circuit, voltage add up, they should be equal to the EMF that is being supplied. Part B, a battery has an EMF of 4 volts, and now they've given you the concept of internal resistance, which is 0.35, which is over here. The battery is connected to a uniform resistance wire XY. Wire XY has a resistance of 0.9 ohms. The potential difference across the wire is 1.8. So they're telling you the voltage across the wire. They're telling you the resistance of the wire. Easy question number one. What is the current in the wire? So you know that current is voltage over resistance. The voltage is 1.8 and the resistance is 0.9. So if you do 1.8 over 0.9, you will get 2 amperes. The number of free electrons that pass a point in 45 seconds. Again, the same thing that we were trying to tell you over there, that the formula for current is NE over T. They've given you the current, which is 2, and you want to find electron charge is 1.6 into 10 minus 19, and the time is 45 seconds. So 2 into 45 divided by 1.6 into 10 minus 19. And your answer should be 5.6 into 10 raised to power 20. The resistance R, they're talking to you about this fixed resistor. Now, answer this question for me. You have the voltage drop across this wire, correct? And what is this voltage drop? This voltage drop is 1.8 volts. You have the current in the circuit because it's a series circuit again. So the current that you got of 2 amperes is actually going through the wire, through this and through this, correct? So 2 ampere current is going to go through the wire, you get this voltage drop. 2 ampere current is going to go through this resistance. There will be some voltage drop, we don't know. The 2 ampere current will also go through this resistance. What will be the voltage drop over here? Can somebody answer this question? What will be the voltage drop over here? So the voltage drop over here, you can calculate it by doing V is equals to IR. I've written small r because it's an internal resistance. Otherwise, you can write capital R as well. So 2 into 0.35 gives you what? 2 into 0.35 gives you 0.7 volts. Now apply this law. Apply what you just wrote. This is a closed loop. So the sum of EMFs, there's only one cell. So the sum of EMFs is 4. I'll write down the voltage law again. Sum of EMFs should be equal to the sum of potential drops. Sum of EMFs is 4. It's not changing. It is fixed. is equals to. Now, what is the voltage drop in this part? The voltage drop in this part is 1.8. What is the voltage drop in the fixed resistor? I don't know. There must be some voltage drop, but this is what we have to find. And the voltage drop, I don't know, across the fixed resistor, plus the voltage drop in this internal resistance was 0.7, so I can get plus 0.7. Can I find out the voltage across the resistor? Yes, of course. So you'll do 4 minus 1.8 minus 0.7, and you will get 1.5 volts. This is the voltage across this resistance. So this is 1.5 volts. I hope so far so good. But that's not the question. The question is, you have to find the resistance. Do you know the current going through this? The current is 2 amperes. So you can use V is equals to IR, which is equals to 1.5. The current is 2. You have to find the resistance, and this is 1.5. So the resistance will be 1.5 divided by 2, which is 0.75 ohms. So that is the answer. And you could do it by a different way as well. I just thought that I should take up a very basic way. So I did it by that. Now, the cell of EMF 1.2 volt is connected in the circuit. This cell is now added from here. Listen to me very, very carefully. When you connect your cell over here, does it have anything to do? Does this voltage have anything to do with this line? No. This is a separate cell. It has its own voltage, 1.2 volts. Now, if they say that you've put it at point P, fine. What was the voltage across the whole length XY? Let's do it like this. What was the voltage across the whole length XY? If you go back, you knew the voltage across XY was 1.8 volts. So voltage across XY is 1.8 volts. And you should know that whenever you have wires, your voltage is always proportional to the length. You should always know that. Your voltage is always proportional to the length. So this voltage of 1.8 volts is proportional to the whole length of XY. What they're saying now is, this is proportional length XY, that you move the connection along the wire. The galvanometer reading is 0 when the distance XP is 0.3. Please try to understand this. When this distance is 0.3 meters, this galvanometer reading is 0. Why? Why? Because this part of the wire has a voltage on it, and this voltage is coming because of this cell. This voltage is 1.2 volts. Why? How do I know? I know because they've said that the galvanometer reading is 0. This voltmeter reading has to be 1.2 volts. This is called the null method. I've got videos on this in my YouTube. You can watch it from there. But you should know that whenever the galvanometer reading is 0, then the cell and the 2 points between which the cell is connected, those 2 points will have the same voltage. So that means that this length of 0.3 meters is representing a voltage of 1.2 volts. And voltage is proportional to length. Now they're asking to calculate the full length XY. So 1.8 in front of L and 1.2 in front of 0.3, just cross multiply. 1.8 into 0.3 should be equal to L into 1.2. And when you do the math, 1.8 into 0.3 divided by 1.2, you will end up getting the length as 0.45 meters. I have a question for you. If I move this jockey from here to here, do you think this voltage will remain 1.2 or will it change? Obviously, the voltmeter is now connected here and there. Will the voltmeter reading change? Yes, because voltage is proportional to length. Would the galvanometer reading still be 0? No. The galvanometer is only 0 when this voltmeter reading and this battery's EMF, they match. If you move point P over here, if you move P to the right, that means that you're increasing the length. You're increasing the length. And when you increase the length, that means that your voltage will also increase. Which voltage? This voltage. And then if this voltage increases, it will no longer be equal to 1. This 1.2 is fixed. So in this case, if you move P to the right or to the left, the voltmeter reading will not be 1.2. If you move this to this side, the voltage will be less than 1.2. If you move it to this side, it will be more than 1.2. I can write it down. The voltmeter reading will be greater than 1.2 volts, and the galvanometer deflection will not be 0. The fixed resistor is replaced by, they're changing the question. The fixed resistor is replaced by a different fixed resistor of resistance greater than R. Okay. So this resistor is being replaced by another resistor of greater resistance. Okay, let's rub everything and focus on the next part. So they're increasing this resistance. So first of all, please tell me what is going to happen to the current in the circuit. The current in the circuit will decrease. That's the first thing. So state and explain the change, if any, that must be made to the position P, again the same question, so that the galvanometer reading is still 0. So what's going to happen to the current? The current in the circuit, you have to explain the theory. Current in the circuit will decrease. Okay. If the current in the circuit is decreasing, what will happen to voltage XY? What will happen to this voltage? This voltage XY. The length of XY is fixed. The resistance of XY is fixed. But the current is less. So what's going to happen to the voltage? Voltage XY will decrease. Correct? Now if voltage XY will decrease, naturally voltage XP, XY has decreased. What's going to happen to XP? XP is a smaller length. XP will also go down because it's of the same wire. If the voltage across this wire has gone down, the voltage between X and P will also go down because it's the same wire. And the galvanometer reading will not be 0 because I just told you. It can only be 0 when this voltage of 1.2 volts, which is this battery's voltage, that matches the voltage across this part. But we just said that voltage XP is going to decrease. Why? Because voltage XY is decreasing. But we want the galvanometer reading to be 0. So what should we do? We should increase the length. Hence, point P should be moved right, or you can say towards Y. Hence point P should be moved right. You could also say towards Y. So that voltage XY increases and becomes equal to 1.2 volts. I hope that makes sense. So the voltage, the current in the circuit decreases. Hence the voltage XY completely decreases. Voltage XP is a part of XY, so voltage XP will also decrease. Now you have to move point P forwards so that the length increases. When the length will increase, I've already told you this. When the length XP will increase, the voltage will increase and it'll come back to the same level as it was before. So if your question is, why did it even drop? The reason is that was the question. They increased this resistance, which caused a decrease in the current. Hence, voltage XY dropped. Why did voltage XY drop? Because resistance XY is constant. That is not changing. How do I know it's constant? R is rho L over A. Have they changed the length of XY? No, the length is constant. Have they changed the area of XY? No, the area is constant. Have they changed the wire? No, So hence the resistance of XY is constant. And V is equals to IR. If this thing resistance is constant, you know that voltage is proportional to current. So when your current decreased, what happened to the voltage XY? The voltage XY also decreased. That's how we conclude it. Then XP is a part of XY, so voltage XP also decreased. And this voltage is still remaining at 1.2, and you want this to be 0. That means that XP should have a voltage of 1.2. That's the only point when this thing will be 0. So where should P go? Left or right? P should go right, so that this length increases. When this length will increase, the voltage will increase, and this voltage will then become equal to 1.2 again, and the galvanometer reading will be 0. I hope that makes sense. Now, a cell of EMF 0.48, this is the third question. A cell of EMF 0.48 volts is connected to a metal wire X as shown. The cell has some internal resistance. We don't know. The current in the cell is 0.8. And the wire X has this length, this area, and this resistance. Calculate the charge passing. Charge passing. Q is equals to IT. So Q is equals to the current, which is 0.8, and the time is 7.5 minutes. Convert minutes to seconds. So 0.8 into 7.5 into 60, and you get the charge as 360 coulombs. Calculate the percentage efficiency with which the cell supplies power to X. So basically, percent efficiency with which the cell supplies power to X. Efficiency. What is efficiency? Efficiency is your useful power output. Useful. So this is going to be the power in wire X over the power input. This is the power supplied by the cell into 100%. Okay. Now we have the current, which is 0.8. Do we have the resistance of wire X? We do. So can I use the formula I square R? Because I have the current and I have the resistance divided by the power supplied by the cell. I have the EMF of the cell. So I have the EMF, and I can multiply it with the current using the formula P is equals to VI. And if I use EMF, then this is going to give me the power of the cell, because the EMF is of the cell. I hope that makes sense. So into 100%. You can simplify it over here, or you can just plug in the value. So 0.8 square into the resistance of the wire, which is 0.4, divided by the EMF of the cell, which is 0.48, into 0.8 into 100%. Let's see. 0.8 square into 0.4 divided by 0.8 into 0.48 into 100%. You'll get 66.66, which is like 67%. Part C, the number of free electrons. Again, number density n. So number density n would be the number of charges per unit volume of the wire. Look at the unit. That's number density. Now, what are the number of charges that you have? The number of charges in the wire are 3.2 into 10 raised to the power 22. They've given that. Volume of the wire. Volume of the wire will be base area into height. Do we have the cross-sectional area? Yes. Do we have the length? Yes. So we can get the volume. So 1.3 into 10 to the minus 7 into 3. 1.3 into 10 to the minus 7 into 3. So 1.3 into 10 to the minus 7 into 3. And 3.2 into 10 to the power 22 divided by the answer. And your answer is going to be 8.25 or 8.2 into 10 raised to the power 28. 8.2 into 10 to the power 28. What is the average drift velocity? I is equals to NAQV. Do we have the current? Yes, of course. We had the current, which was 0.8. Do we have this is actually number density, charge density. Number density, charge density. So this value is 8.2 into 10 raised to the power 28. Do not confuse this with the number of free carriers. Number of free carriers are something different, which is 3.2 10 to the power 22. Into the area was 1.3 into 10 raised to power minus 7 into the charge q, which is 1.6 into 10 raised to power minus 19 into the drift velocity. So always remember to use the fraction mode, as I always say, the fraction mode. You put your values in the numerator over there and the denominator and always get the right answer. So 0.8 divided by my answer to the previous part into 1.3 into 10 to the power minus 7 into 1.6 into 10 to the power minus 19. And I'm getting 4.68 into 10 raised to the power minus 3. So 4.7 into 10 raised to the power minus 3 meters per second. Wire Y has the same, so this is a different wire. Wire Y has the same cross-sectional area as wire X and is made of the same material, but it's longer. So same cross-sectional area, A and rho are the same, but it's longer. So resistance is, which is rho L over A, rho and A are constant. So can I say resistance and length have a direct relationship? Of course we can. They do have a direct relationship. All right, the wire X in the circuit is now replaced by wire Y. So basically, again, what you're doing is that you're increasing the resistance because the length is more, the resistance will be more. So because the resistance is proportional to length, hence resistance of the circuit increases. Okay. So what should happen to the current in the circuit? The current in the circuit decreases. Now, when the current in the circuit decreases, they're saying whether the drift velocity would be more or less. What is the formula for drift velocity? NAQV. Current has gone down. Number density, it's the same wire, same material. So number density is same, area is same, charge is same. So current and drift velocity have a direct relationship since current is proportional to drift velocity. And I can say that N, A, Q are constant. Hence, the drift velocity decreases. I hope that this makes sense, and that is the end of this worksheet.